Every moment you're awake and every moment you're asleep, you're being blasted by an invisible stream of tiny bullet hits from the sun, from your screen, from distant galaxies, and you never feel a single one of them. They move at light speed. They don't age. They bend around gravity. They show up as clean clicks in detectors. And when you really push them, they start breaking your idea of what path, time, and even reality mean. In this video, we're going to chase down what those hits actually are, photons, and step through how these so-called particles of light go from something as ordinary as a lamp in your room to something so strange that even physicists have to stop and remind themselves what the math is really saying. But before we continue, please subscribe to the channel to give your support. Let's continue. Each photon carries a tiny amount of energy. So tiny that your skin never feels any single one of them on its own. Your body only notices the sum, the thermal effect, the heating. Your eyes only notice the sum, the continuous signal. That is why your experience of light is smooth. Your senses average over ridiculous numbers of hits and hand your brain a clean brightness level instead of a grainy count. This is where your intuition starts to mislead you. Your brain likes to treat light like a steady fluid, something that can be made weaker or stronger without any internal structure. Turn up the brightness, it feels like more of the same stuff. Turn it down, it feels like less of the same stuff. But the more carefully you look, the more obvious it becomes that this is not how nature is working. Light energy is quantized. That word just means chopped into indivisible units. Take a blue photon with a wavelength around 450 nanometers. That is 450 billionths of a meter, about half of a thousandth of a millimeter, or roughly 150,000th of an inch. One blue photon at that wavelength carries about 4.4 times 10 to the minus 19 joules of energy. You need something like 2.3 times 10 to the power of 18 of those to add up to one single joule. 1 joule is just the amount of energy it takes to lift a small apple by about 10 centimeters, a few inches. So 1 apple lift worth of energy in blue light is already a multi-quintillion photon event. When you look at a bright screen or a sunny window, your visual system is dealing with astronomically large photon counts per second, and that is why it looks continuous. Your eyes are basically never in a regime where individual photons stand out from the crowd. So here's the problem that physicists hit around the year 1900. Everyday experience says light is smooth, but some very specific measurements were screaming, no, it is not. And the thing that exposed this most brutally was not a star or a laser, it was a hot box. Physicists built idealized blackbody ovens. These are cavities with small holes designed so that almost all radiation that enters gets absorbed, and the light that leaks out of the hole is a very pure sample of thermal radiation. You take one of these, heat it to a known temperature, maybe 1000 degrees Celsius, about 1800 degrees Fahrenheit, and you measure how much power you get at each wavelength. Plot that and you get a smooth curve. It rises with wavelength, hits a peak in the infrared, then falls off at short wavelength. No weird spikes, no runaway behavior. Classical theory at the time tried to predict this curve. Using continuous energy assumptions, you count all the possible ways electromagnetic waves can exist inside the box, and you let them take any energy they like. When you do that, the math says something insane. As the wavelength gets shorter, the amount of energy radiated should grow without bound. Shorter wavelength means higher frequency, and the theory just keeps dumping more and more energy into those high frequencies. That gives you infinite total energy, which is obviously not what you see in the lab. This failure even got a name, the ultraviolet catastrophe, because the divergence happens in the ultraviolet part of the spectrum if you push the equations there. But the experiments did not care about the theory's predictions. In the lab, a 1000-degree oven has a peak at a few micrometers. A hotter surface, like the sun at about 5800 Kelvin, or roughly 10,500 degrees Fahrenheit, has a peak in the visible range. Nothing goes to infinity, the curve just shifts and reshapes in a specific, repeatable way. The old equations could not match that behavior, no matter how people tune them. Max Planck stepped into this mess with one radical move. He introduced a new fundamental constant, now called Planck's constant. Its value is around 6.6 times 10 to the minus 34 in units of joule seconds. Then he made a very specific claim about light and energy. For any given frequency of light, energy cannot change smoothly. It can only change in steps. Each step has a size equal to Planck's constant multiplied by the frequency. So instead of waves inside the oven taking on any energy, they can only take on values that are whole multiples of this basic chunk. That sounds like a small tweak, but it completely changes how the math behaves. When you recalculate the black body spectrum with this quantization rule in place, the predicted curve suddenly lines up with the measurements. The peak appears and moves with temperature exactly as the data shows. The tail at short wavelengths no longer blasts off to infinity, it falls off in the way experiments had already recorded. When physicists plugged in the temperature of a filament lamp, about 2700 Kelvin, or roughly 1400 degrees Fahrenheit, the resulting theoretical spectrum matched the real light from the filament. When they used the sun's surface temperature, the peak in the middle of the visible range, right where human eyes are most sensitive. That last point is worth spelling out. Your eyes are not sensitive to all wavelengths equally. They respond most strongly to a band roughly centered in the green-yellow part of the spectrum. That peak sensitivity overlaps almost perfectly with the peak in the sun's emission spectrum at Earth's distance. In other words, evolution tuned your vision hardware to the dominant photon output of a G-type star. Photons shaped your sensory hardware. You see normal daylight only because your biology learned to read that specific distribution of photon energies efficiently. All of this was a huge win for matching theory to experiment, but Max Planck himself was uncomfortable with the idea that these energy chunks might be physically real. At first, he treated quantization as a formal trick, a way to get the right answer. Then, within a few years, Einstein pushed the idea much harder in the context of the photoelectric effect, treating light as if it really comes in individual packets when it hits metal and knocks out electrons. Piece by piece, the community was forced to accept that photons are not just a convenient way to write equations, they're actually how light behaves. And that leaves you with a very sharp question. If light is made of these discrete photons, each with energy set by its frequency and Planck's constant, what are these things doing between the oven wall and your eye, or between the sun and Earth? Are they flying along definite paths like tiny bullets? Are they spread out like waves? How can they be both when your detectors only ever see single localized hits? So the next set of experiments attacks exactly that point. You slow the light down, you send photons one by one, you give them a simple choice between two paths a tiny distance apart, and you watch where they land. That is where the double-slit setup comes in, and where the behavior of just one photon at a time starts to break the basic category of particle that your brain relies on. Here is the experiment that blows up your normal idea of what a particle is. No philosophy, just hardware on a table, a few meters of distance, and results that refuse to fit into common sense. You take a source that can send out single photons, one by one. Labs use things like special crystals, quantum dots, or single atoms to do this. But the key part for you is simple. The emission rate is so low that on average, there is less than one photon in flight between the source and the detector at any moment. Over about 1 meter, roughly 3 feet of distance, the space between them is usually empty. In the middle, you place a barrier with two extremely narrow slits cut into it, separated by a few micrometers, so a few millionths of a meter, or about a few 10,000ths of an inch. Behind that, maybe another meter away, you set up a detector screen, something like a highly sensitive CCD, similar in principle to what sits behind your phone camera, but cooled, shielded from stray light, and tuned to pick up single photon hits. So the geometry's clear. Source, two-slit barrier, detector. The slits are close together compared to the distance to the detector, and their width is on the same order as the wavelength of visible light, a few hundred nanometers. The source sends one photon, it travels towards the slits, something happens at the barrier, and then, if it makes it through, it hits the detector. Now the obvious question, when a single photon arrives, what does the detector actually show you? Each time a photon gets detected, you do not see a fuzzy smear spread over the screen. You see one localized event. In a CCD, that's a single pixel, or a tiny cluster of pixels registering charge. In a photomultiplier tube, that's a single electrical pulse. It has a position, a timestamp, and that's it. One photon, one click. That is very particle-like behavior. The photon did not show up in 10 places at once. It ended up at one spot, slightly blurred only by the limits of the optics and detector resolution. The wavelength might be around 500 nanometers, half a micrometer, roughly 1/50,000th of an inch, but the impact location is still a definite point on a screen maybe 10 or 20 centimeters across, 4 to 8 inches. If you send, say, 100 photons and mark every hit, you just get a cloud of dots, noisy and scattered. Nothing weird yet. It looks like someone firing tiny pellets with some spread in their aim. So far, you could still say, fine, the photon is just a little bullet that takes one path or the other through the slits and lands somewhere on the screen. But what happens when you keep going and instead of 100 photons, you record 100,000, a million or more? You let the setup run. Photon after photon leaves the source, crosses the gap, interacts with the slits, and either hits the detector or gets absorbed. Every event is still a single dot, but when you overlay all those dots, a pattern starts to emerge. The screen does not just fill in smoothly. You see bright bands where hits are common, and dark bands where hits are rare or almost absent. That is an interference pattern. The same kind of pattern you get from water waves or sound waves when they overlap and reinforce or cancel each other out. The spacing between these bright fringes depends on the wavelength of the light, the distance between the slits, and the distance to the screen. With visible light, slit spacing on the order of a few wavelengths and a screen about a meter away, the bright bands end up separated by distances in the millimeter range, maybe a millimeter or two apart, a tiny fraction of an inch. You can literally measure this with a ruler. The key point is brutal. The pattern you see matches the pattern that a wave of that wavelength would produce, not the pattern you would predict from classical particles fired randomly through two openings. So you're stuck with a hard statement. Each photon arrives as a single localized hit, but the distribution of many hits builds a wave-like interference pattern. And you can't escape the fact that you are sending them one at a time, with less than one in the apparatus at once. They are not bouncing off each other to create the fringes. The only way to match the data is to accept that each photon behaves between emission and detection as something spread out that can interfere with itself. That clashes directly with the bullet picture. If a photon really were just a tiny object that always went through either the left slit or the right slit, like a grain of sand, you wouldn't get interference fringes. You would get the sum of two single slit patterns, a broad distribution with no fine bright and dark stripes, but you get the stripes. So something in your which slit did it really go through story is already in trouble. Maybe you think the experiment is somehow biased by having both slits open. So the next move is simple. Keep everything the same, but close one slit. With both slits open, you saw a full interference pattern, alternating bright and dark bands, separated by millimeters. Now you block one slit, say the right slit, so photons can only pass through the left opening. The source, distance, wavelength, detector all stay the same. The energy is the same. The speed is still light speed, about 300 million meters per second, roughly 670 million miles per hour. The only change is that you removed the second possible path. The hits keep coming, one by one, but the pattern they build is now different. The sharp, bright, and dark interference fringes vanish. Instead, you get a single broad hump, a diffraction pattern from one slit. Open only the right slit, same thing, just mirrored. Open both again, the sharp fringes return. The number of photons per second does not matter. As long as you stay in the single photon regime, the logic holds. So just having two possible paths available completely changes the statistics of where photons land. Even when you fire them one at a time, the pattern you get with both slits open is not the sum of the one-slit patterns. It is something extra, created by the wave-like nature of the underlying quantum state. The presence or absence of that second slit is not just about more or less light. It changes the entire structure of the outcomes. This leads you to a very uncomfortable corner. At the detector, the photon behaves like a particle, one hit at one place. In flight, its behavior must be described by something that goes through both slits at once, spreads out in space, and interferes with itself. You cannot keep a simple, classical picture that works everywhere. You need two different descriptions, wave and particle, and neither of them is fully right on its own. The natural instinct at this point is to ask a very direct question. Okay, but which slit did the photon really go through? You want to attach a definite path to each click. You want to say, that dot came from the left slit, that one from the right slit. The double-slit interference pattern looks like it is hiding that information from you. So you try to force the issue. You try to watch the photon as it passes the barrier. And here is where things get worse. Because the moment you add any reliable way to find out which slit each photon uses, the interference pattern collapses. Just the act of making the path information knowable, even if you do not literally read it out every time, changes the distribution of hits on the screen. The universe switches from wave-type behavior with fringes to particle-type behavior with no fringes, just because you gave yourself the option to know the path. How does that work in detail? What does it mean for a measurement device sitting at the slits to destroy a pattern built up meters away on the detector? And why does this happen even when photons are still arriving one at a time? That is the step where weird turns into deeply hostile to your normal idea of cause and effect, and where the role of measurement in quantum mechanics starts to dominate the story. So what actually happens when you force a photon to confess which slit it used? You'd think the answer would just add detail to the story you already have. Instead, it wipes out the pattern that made the whole experiment interesting in the first place. To get which-way information, you attach something to the slits. You can put tiny detectors near each opening, photodiodes that fire if a photon goes past. You can use atoms that flip from one state to another when a photon interacts with them. You can put polarizers so that a photon going through the left slit gets one polarization and the right slit gives it a different one. The exact gadget doesn't matter. The logic is the same. After the photon passes the barrier, in principle, you can look at the state of that gadget and say it went left or it went right. Now look at the screen again. You still fire photons one by one. You still have both slits physically open. The detectors do not block the paths, they just tag them. But the bright and dark interference fringes vanish. Instead of a clean pattern of alternating high and low counts, you get a distribution that looks like classical particles going through one slit or the other and spreading out. The statistics of where photons land have been rewritten just because path information is available. The important detail is this: you don't even need to read the which-way information every time. The fact that the information exists in principle is enough. As soon as the world can, in theory, store this photon used the left slit, the interference pattern that required photon went through both disappears. The measurement setup has changed what kinds of outcomes are allowed. You did not change the photon's energy, or its speed of about 300 million meters per second, around 670 million miles per hour. You changed the questions you are able to ask, and the universe changed the answer it gives you. So that raises a sharper question. Does the photon decide to be a wave or a particle at the moment it leaves the source, or does that decision only lock in when you define the measurement context? This is where delayed choice experiments come in. The basic move is simple but brutal. You set up a system where the photon has to pass the slits first, travel some distance, and only then do you decide whether to keep or erase which way information. You might use extra beam splitters, polarizers that can be inserted or removed, or devices that can erase polarization tags before the photon reaches the final detector. The timing is tight. The choice is made after the photon has already passed the region where it would have to choose a slit in any classical picture. Over meter-scale paths with electronics that switch in nanoseconds, you can ensure that there is no way for a signal traveling slower than or at light speed to carry your later choice back to the earlier slit event. Yet the data still follows the same rule. When the final setup preserves which-way information, the interference pattern disappears. When the final setup erases which-way information, even if the photon had already gone past the slits, the interference pattern returns in the statistics. So the behavior you see at the detector is not fixed at emission. It depends on what kind of measurement you allow at the end. The universe doesn't commit to this photon went through slit A or through slit B in a simple classical way before the measurement context is defined. It only commits when the whole experiment, including your possible questions, is taken into account. That's why people say the photon doesn't decide to act like a wave or a particle until measurement. It's not that it changes its mind, it's that your old categories don't apply cleanly between source and detector. At this point, you might think, okay, but maybe this is all some weird artifact of bad equipment or noisy sources. Maybe the light isn't really single photons at all. If that were true, the whole story would fall apart. So the next step is to look at the hardware itself. Modern labs build genuine single photon sources. They use quantum dots, which are tiny semiconductor structures acting like artificial atoms. They use trapped ions held in electromagnetic fields. They use nonlinear crystals where one higher energy photon converts into two lower energy photons in a controlled way. These devices can be driven so they emit one photon at a time, with repetition rates from thousands of times per second up to millions of times per second. On the detection side, there are avalanche photodiodes and superconductor nanowire detectors with efficiencies above 90%. Dark counts, which are false clicks with no photon, can be pushed down to just a few per second. Experiments carefully subtract that residual noise. When you see interference patterns and their disappearance under which-way tagging, you are not seeing an artifact sitting on top of a big, messy background. You are seeing clean behavior of individual quanta under tight control. So you now have three facts that all have to be true at once. 1, you can send photons one by one. 2, with both slits open and no which-way information, their hits build a wave-like interference pattern. 3, as soon as which-way information is available, even indirectly, the interference pattern vanishes, and the pattern looks like simple particles again. The weirdness is not in your lack of control. It's in how the world itself responds to what can, in principle, be known. This leads you straight into a trade-off that is not just a vague idea, but a quantitative rule. As you design more and more clever experiments, you find that the clearer the path information becomes, the weaker the interference pattern gets. If you set things up so you can almost perfectly tell whether the photon used the left slit or the right slit, the fringes become almost completely washed out. If you arrange the apparatus so path information is very fuzzy or impossible to recover, the fringes come back sharp and strong. Physicists talk about two quantities here: how distinguishable the paths are and how visible the fringes are. Distinguishability is about how well you can, in principle, tell which path was taken. Visibility is about how deep and clear the bright and dark bands on the screen are. The product of these two is bounded. Push one towards its maximum and the other must drop. You cannot have perfect path knowledge and perfect interference at the same time. This is the same core idea as the uncertainty principle. Certain pairs of properties simply cannot both be sharp at the same time. So now look at what this does to your mental picture of a photon. The particle story says it has a path. It is here, then here, then here. The wave story says it spreads out and interferes. The double-slit and measurement experiments tell you that you cannot promote either story to the full truth. Depending on what questions you ask and what information the environment can store, the photon shows you only one side at a time, and the other side is suppressed. That should kill the last comfortable image of a photon as a little ball with some mass flying along a track. And it also blocks the idea of a classical wave that just happens to be in small chunks. The photon lives in a regime where position, path, and wave character are tied together in a way that your everyday language cannot cleanly capture. So the obvious next question is, if a photon is not a tiny lump of stuff moving on a classical path, what can you say about its motion at all? How does something with no rest mass that always moves at light speed actually experience its own journey from source to detector? And what does that do to your usual picture of time and distance? Answering that forces you to bring in relativity and talk about what it means to live permanently at light speed, where proper time drops to zero and distances behave in a completely non-intuitive way. You want to know how a photon moves, but here's the catch. It never slows down, it never sits still, and in a very real sense, it never experiences time at all. So what does motion even mean for something like that? A photon has zero rest mass. That means if you try to imagine it sitting still, the math just breaks. That state is not allowed. Special relativity says there's one special speed in the universe, the speed of light in a vacuum, about 300 million meters per second, around 300,000 kilometers per second, or about 186,000 miles per second. If you give any normal particle more and more energy, its speed approaches that limit, but never quite gets there. A photon starts there. Its entire existence is tied to that one speed. Its energy is proportional to its frequency, with Planck's constant as the proportionality factor. So higher frequency means higher energy. Its momentum is just that energy divided by the speed of light. So even though it has no rest mass in the usual sense, it still carries energy and momentum. It can still push on things. It can still transfer a kick when it hits matter. At 300,000 kilometers per second, a photon could go around Earth more than 7 times in 1 second. There is nothing in your everyday experience that sits in that regime. So what does that insane speed do to the photon's experience of time? For slower objects, special relativity gives you time dilation. If something moves very fast relative to you, its onboard clock runs slower compared to yours. At, say, 90% of light speed, this effect is already huge. As you crank the speed closer and closer to the speed of light, the amount of time that passes on the moving clock compared to the time you see shrinks and shrinks. In the equations, the factor that controls this grows without bound as the speed approaches light speed. In the limiting case, where the speed is exactly the speed of light, the proper time along that path goes to zero. Proper time is just a time measured by a clock moving with the object. For a photon, in that limiting sense, that clock would not tick at all. From your point of view, a photon can travel for billions of years. Light from the early universe, from almost 13.8 billion years ago, can cross the expanding cosmos today. You see that as an ancient journey, older than any star you know, over a distance of billions of light years. But if you try to talk about the photon's own proper time, the answer is extreme. Between emission and absorption, it experiences no passage of time. Those two events, which you see as separated by billions of years, are, from that limiting perspective, pressed into a single instant. In your frame, the photon left some hot plasma shortly after the Big Bang and arrived now. In the photon's own sense, there is no then and now, there is just the emission-absorption pair as one act. There is an important caveat here. Strictly speaking, relativity does not allow you to set up a rest frame that moves alongside a photon, because you can never travel at light speed yourself. So when physicists say from the photon's point of view, they really mean in the limit as you approach light speed, the proper time along that kind of path goes to zero. But the physical takeaway is still clear. The closer you get to light speed, the less time you accumulate on the clock moving with you, and a photon is permanently at that extreme edge. If the passage of time collapses like that, what happens to distance? Relativity gives you length contraction. Distances along the direction of motion shrink for the moving object. Take a spaceship flying past Earth at 99% of light speed. In its own frame, the distance between stars along its path is shorter than what you measure from Earth. Push the speed closer to the speed of light, and the contraction becomes more severe. In the same limiting argument as before, if something could ride along at exactly light speed, distances along the direction of travel would contract towards zero. So when you detect the photon that left the galaxy 10 billion light-years ago, you see a journey across roughly 10 billion times 9.5 trillion kilometers each, so about 9.5 times 10 to the 25 meters, a number so large it is hard to relate to anything. That's about a billion kilometers. From your viewpoint, that path is enormous. But in the limiting light speed picture, the distance along the photon's world line is crushed. Emission and absorption are right on top of each other in proper distance, just like they are right on top of each other in proper time. Put those two pieces together and you get a weird statement. For you, the photon travels through space and time, covering huge distances and taking ages. For the photon, in the sense given by the equations, there is no time interval and no spatial separation between its start and end events. It never ages, it never experiences a trip. It's just part of a connection between 2 points in spacetime. That's completely outside the way you think about a thrown ball or a flying airplane. Now, even with time and distance behaving like that, photons are not all the same. They come in an enormous range of energies and wavelengths. At one end, you have radio photons. Their wavelengths can be meters, kilometers, even thousands of kilometers, so miles and thousands of miles. Each of those carries a very small amount of energy, around 10 to the negative 27 joules in some cases. That's unbelievably tiny. You would need a ridiculously large number of them just to heat up a grain of sand by a noticeable amount. At the other end, you have gamma-ray photons from extreme astrophysical events. These can have energies around 10 to the negative 13 joules or higher per photon. That still sounds small, but compare counts. If you had 1 trillion of those, that's 10 to the 12 photons, the total energy could reach a scale where you can start comparing it with macroscopic kinetic energies, like the energy of a pitched baseball moving at around 40 meters per second, about 90 miles per hour. The exact numbers depend on the details, but the point is simple. Just by changing the frequency, you can move photon energies across more than 20 orders of magnitude, from feeble radio photons to intensely energetic gamma bursts. And yet, they all share the same basic properties. Zero rest mass, always moving at light speed, still described as quanta of the same electromagnetic field. So you end up with this picture. A photon doesn't have a rest frame. It doesn't accumulate its own time. Its path length along its motion direction contracts in the limit down to almost nothing. And yet, it carries real energy and momentum, and can span a range from kilometer-scale radio waves to intensely energetic gamma bursts. It acts like a sort of timeless messenger, but still delivers a very real physical punch when it interacts with matter. That should already be enough to tell you a photon is not a simple, tiny ball of light coasting through space. No normal object you deal with lives in this regime, where time and distance collapse in that extreme way, but energy and momentum remain well-defined and measurable. The photon fits into relativity by living right at the boundary, at the maximum speed, with zero rest mass and no proper time. So here's the next twist. If a photon never sits still, if it never has a rest frame, and if what you call its path is really just a connection between emission and absorption events with zero proper time between them, then trying to treat it like a little self-contained object was probably the wrong starting point. Modern physics takes a different route. It begins with the idea that there's an electromagnetic field filling all of space, at every point, all the time, and photons are just the smallest possible excitations of that field. In other words, instead of tiny beads flying through empty space, you have a continuous field everywhere, and a photon is what you get when that field is excited in a specific quantized way. That move, from particles first to fields first, is the next big upgrade you have to accept if you want a serious answer to what a photon really is. Here's the next hard step. The photon is not the starting point. The photon is what you get after you accept that something else, more invisible and more basic, is already there everywhere, even in empty space. Modern physics starts with fields, not with particles. There is an electromagnetic field filling every cubic centimeter of space, every sugar cube-sized chunk of volume, whether or not you see any light. When there is no light, the field is in a lower energy state. When there is light, the field is excited in specific ways. A photon is one unit, the smallest possible step, of that excitation. So you are not really throwing a little object through nothing, you are changing the state of a field that already lives at every point between source and detector. So how do we know this field is real and not just a mathematical trick? Go back to the classical description first. In the 19th century, James Clerk Maxwell wrote down a set of equations that tie electric and magnetic effects together. When you solve those equations in empty space, you find that disturbances in the electromagnetic field move as waves at a specific speed. When you plug numbers in, that speed matches the measured speed of light in vacuum, about 300 million meters per second, around 186,000 miles per second. That is a big clue. Light is not a separate substance, it is an electromagnetic wave. Those waves can have wavelengths ranging from nanometers, billionths of a meter, all the way up to kilometers and beyond. In the lab, if you build antennas separated by meters or feet, drive them with oscillating currents, and measure the radiation pattern, the behavior you see matches Maxwell's predictions. Radio transmitters, Wi-Fi, microwave ovens, radar, all of that is just engineering on top of those equations. So, classically, the electromagnetic field is already a very successful description of reality. You push it, it pushes back, the math matches the data. But the classical version treats energy as continuous. It lets the field take any energy value. That picture is exactly what fails in the blackbody problem you saw earlier. It is also what fails in the photoelectric effect, where light kicks electrons out of a metal only if each photon has enough energy, regardless of how weak the overall beam is. So the next question is obvious. Can you keep the field idea but fix the energy problem? Quantum electrodynamics, QED for short, does that. The move is conceptually simple but technically heavy. You take the classical electromagnetic field and treat each independent pattern of vibration as a quantum system. Each pattern, or mode, is like a simple harmonic oscillator in quantum mechanics. A harmonic oscillator is just a system that can vibrate back and forth, like a mass on a spring. In quantum mechanics, that kind of system does not have a smooth range of possible energies. It has a ladder of energy levels. The spacing between the levels depends on the frequency of the vibration, and each step between neighboring levels has a fixed size set by Planck's constant times that frequency. Translate that into field language. For every mode of the electromagnetic field with a given frequency and spatial pattern, there is a ladder of allowed energies. The lowest energy is not zero, it's half of that basic quantum step. Then comes 1.5 steps, then 2.5, and so on. Moving from one level to the next higher level is what we call adding one photon to that mode. Moving down is removing one photon. So in this view, a photon is not a dot flying around, it is the system jumping from one energy rung to the next. This is not just word games. When you say a laser has a certain wavelength and a certain power, you can literally count how many photons per second that corresponds to. For a typical cheap laser pointer, a few milliwatts of power at visible wavelengths translates to roughly 10 quadrillion photons per second. That's 10 to the power of 16. In QED language, that is a huge number of field quanta sitting in the same mode, all in step with each other. That coherence is why laser beams stay tight and produce very sharp interference patterns compared to normal light bulbs. But you could still ask, is this quantized field picture just a convenient calculation tool, or can we see it directly? This is where cavity QED experiments become important. Physicists build cavities using mirrors that face each other with separations of a few millimeters, a few tenths of an inch. The mirrors are highly reflective, so a photon that enters the cavity bounces back and forth thousands of times before it leaks out or gets absorbed. The cavity only allows certain wavelengths to exist strongly inside, like how a guitar string only supports specific notes. Now add atoms to the story. You send single atoms through the cavity, one at a time, moving at controlled speeds. Each atom has internal energy levels and it can interact with the electromagnetic field inside the cavity. The key trick is this. By measuring the final state of the atom, you can infer how many photons are in the cavity mode without necessarily absorbing them. The interaction slightly shifts the atom's energy levels depending on how many photons are present. That shift can be read out with spectroscopy with crazy precision. When you do these experiments, you see discrete jumps. The data lines up with the idea that the cavity field has 0 photons, 1 photon, 2 photons, and so on, not a continuous blur of energy. You see that atoms can add or subtract single photons from the field, and the timing and probabilities match what QED predicts. You can watch Rabi oscillations, where the system cycles between atom excited, no photon, and atom in ground state, 1 photon in the field, at rates that depend on the coupling strength. All of this measured with mirrors a few millimeters apart and atoms flying a few hundred meters per second, a few hundred miles per second, is direct evidence that the electromagnetic field really behaves like a set of quantized modes. The precision of these tests is brutal. The agreement between QED calculations and measured transition rates, frequency shifts, and photon statistics is often better than 1 part in 1,000, sometimes 1 part in 1,000,000 or more. You are not patching a broken theory with a vague story. You are using a field-based quantum theory that spits out numbers, and those numbers match reality to more decimal places than you actually need for almost any technology. So where does this leave the photon in your mental model? Not as a tiny ball of light flying through emptiness, not as a smear that happens to behave like a particle at the detector. The cleaner version is this. There is an electromagnetic field everywhere. When that field is in one of its quantized excited states, you say there is a photon in that mode. When that excitation gets transferred to matter, you see a click in your detector, or an electron jump in an atom, or a chemical reaction in your retina. That still raises another question, though. If a photon is just one quantum of field excitation, can it have any internal structure at all? Does it carry more than just energy and momentum? The answer is yes. It carries angular momentum, it has polarization states, and it can even carry twisted patterns of phase that show up as orbital angular momentum. None of that sits comfortably in a picture of a little bullet. It forces you to talk about direction, spin, and how the field vibrates in space. So the next layer of strangeness is about what a photon can be while it races along at light speed. How can something with no rest frame still have a kind of orientation, a handedness, and the spin with a fixed size? And how do simple tools like polarizing sunglasses and camera filters end up probing those deep quantum properties every single day without you noticing? Here's a detail about photons that looks simple but refuses to fit your normal idea of a direction. A photon has an internal orientation even though it has no rest frame and no little arrow you could ever see. Start with polarization. When a photon moves, its electric field oscillates in a direction perpendicular to its motion. If the photon is moving straight towards you, that field can shake side to side, up and down, or at any angle in between, but always across your line of sight. That orientation is polarization. Horizontal means the field oscillates left to right, vertical means up and down, anything in between is a mix of those two. You hit this in everyday life. Polarizing sunglasses use a layer that only lets through photons whose fields line up in one direction. Light reflected off roads and water is biased towards one polarization, so a correctly aligned filter cuts that glare. Take 2 polarizing filters, line them up, look at a bright scene, you see some white. Rotate one by 90 degrees, leave everything else the same, the brightness drops towards 0. On the photon level, you are not smoothly weakening the beam, you are discarding photons whose internal orientation doesn't match the filter. That sounds like photons carry a tiny built-in arrow, but this is not a literal rod. It's a property of the electromagnetic field mode. For a beam, many photons can share the same polarization, or you can have a mix. For a single photon, polarization is a quantum state that can be put into superpositions, just like spin up and spin down for an electron can combine into something in between. So what is that spin for a photon if nothing solid is spinning? In particle language, the photon is a spin 1 particle, But unlike massive spin 1 particles, which can have 3 spin orientations, the photon only has 2 allowed helicity states, often called left-handed and right-handed. These match left and right circular polarizations. If you freeze a wave pattern and look at how the electric field rotates as the wave moves, one state turns one way, the other turns the opposite way. Do not picture a ball rotating like a planet. That picture's wrong here. Spin is intrinsic angular momentum, a built-in property that shows up whenever the photon interacts. It appears in scattering experiments and in atomic transitions where atoms only absorb or emit photons if the total angular momentum, including the photon's plus or minus 1 unit, balances correctly. The key point is that the photon always carries this fixed amount of spin, never more, never less. You cannot have half a photon of spin. You can change how that spin is oriented relative to the direction of travel, you can mix linear and circular polarization, but the magnitude is locked by quantum rules. Now, how do you actually see polarization at the single photon level, not just as bulk brightness changes? Take a source that emits photons with a well-defined polarization, say at 45 degrees, halfway between horizontal and vertical. Put a polarizer in front that only passes horizontal photons. Each photon that hits that filter has a 50% chance to get through and a 50% chance to be absorbed. You do not get half a photon. You either get a click or you get nothing. Once a photon passes that horizontal polarizer, its polarization is no longer at 45 degrees. It is now definitely horizontal. Send it into a second horizontal polarizer, it goes through with essentially 100% probability. The first measurement has forced the photon into a new state. This is what people mean when they say measurement collapses a quantum state. Here's where it gets non-classical fast. Take 2 polarizers set at 90 degrees to each other, one vertical, one horizontal. No light should pass, and at the photon level, transmission is basically 0. Now insert a third polarizer between them, rotated to 45 degrees. Classically, you might think this extra element only blocks more light. In reality, total transmission increases. Some photons get through all 3 because the middle polarizer rotates polarization states in a quantum way. Adding an extra blocker in the right orientation can make more photons survive, not fewer. And the story does not stop at simple up, down, left, right. You can structure light so that its phase winds around as you move in a circle around the beam's axis. These are twisted photons, carrying orbital angular momentum. The wavefront of such a beam is like a corkscrew, with the phase spiraling around as you go around the center. In this case, the photon's angular momentum is not just its intrinsic spin, it also includes a part from this spatial twist. You can generate these twisted modes with holograms or special optics. Each twist level, labeled by an integer, carries a different amount of orbital angular momentum. In optical communication, you can use different twist states as separate channels, stacking information on top of frequency and polarization. Experiments have sent these beams over kilometers, miles, and then read out the twist structure on the other side. So now you have a photon that's not just some energy moving at light speed. It has a polarization direction that decides whether it passes or dies in a filter. It has a fixed intrinsic spin, and it can carry extra orbital angular momentum in the way its field is twisted in space. When all of that interacts with atoms and materials, it decides which transitions happen, which scattering angles light prefers, and how much torque light can exert on microscopic objects. This should kill any last hope of treating a photon as a simple point particle with no internal structure. You are dealing with a quantum excitation of a field, with orientation, handedness, and twist built in. And even when you think you have no photons, the field does not go silent. It still has residual fluctuations. It still stores energy in its lowest state. And those ghost-level activities show up as real forces and measurable shifts. So the next question is, if you turn off every light source, pump out the air, chill everything down, and call that a vacuum, is there really nothing there? Or do photons in a more subtle virtual form still leave fingerprints you can measure between metal plates, inside atoms, and in the magnetic properties of the electron itself? You look at empty space and call it nothing, but the electromagnetic field doesn't care what you call it. Even when you turn off every light, pump out the air, cool the walls, and do everything you can to make zero, the field refuses to go flat. It keeps a baseline of activity that you can't turn off, and that baseline has real, measurable effects. Start with the idea of zero-point energy. In the field picture, each possible mode of the electromagnetic field is like a quantum oscillator. That means its energy can only take specific values, equally spaced steps. Even in the lowest possible state, the ground state, the energy is not zero. It sits at half of that basic quantum step, the step set by Planck's constant multiplied by the mode's frequency. So take all the modes in a cubic meter of space, from very low frequency radio up to insanely high gamma ray frequencies, and give each of them that half step of energy. When you add all that up, you get a huge energy density per cubic meter. You don't see that as a constant glow because physics only cares about changes in energy between states, not the absolute number. If everything everywhere got shifted by the same amount, most experiments would never notice. But this ground level is not harmless background. When you change the allowed modes of the field, you change the zero-point energy, and that difference shows up as a force or a shift you can actually measure. So the natural question is, can this invisible, untouchable vacuum move real matter around? This is exactly what the Casimir effect shows you. Take two flat, uncharged metal plates, polish them, line them up parallel, and bring them to a separation of a few micrometers, so a few millionths of a meter, about 1/100th the width of a human hair. In that tiny gap, only certain electromagnetic modes fit cleanly between the plates. Outside the plates, all modes are allowed. That mismatch changes the vacuum energy inside compared to outside. When experimentalists measure the force between the plates, they see a very small but real force pulling them together. The force is on the order of piconewtons for small plate areas and micrometer dApps. A piconewton is about the weight of a single red blood cell in Earth's gravity. It's tiny, but with sensitive torsion balances and cantilevers, you can measure it. You can calculate the expected force by summing up the change in zero-point energy of all the modes, or in more intuitive language, by thinking of virtual photons bouncing between and around the plates. The expected force matches the measured force. Nothing is pushing the plates together. Once you accept that, you have to ask what this restless vacuum is doing on much smaller scales, like inside atoms. Hydrogen, the simplest atom, has energy levels that were predicted by the Dirac equation, which combines quantum mechanics and special relativity for the electron. Those predictions were extremely good, but they missed a tiny detail. When physicists measured certain spectral lines in hydrogen at insane precision using microwave spectroscopy, they found a small shift in the energy between two levels compared to the Dirac prediction. This is the Lamb shift. The Lamb shift is small. You're talking about differences that show up only when you can measure frequencies with accuracy better than 1 part in a billion. But it's real, it repeats, and it needed an explanation. Quantum electrodynamics gives you that explanation. The electron in the atom is not sitting in a silent vacuum. It's constantly being jiggled by vacuum fluctuations of the electromagnetic field. These fluctuations make the electron's position and momentum fuzzier than the simple theory allowed, and that slightly alters its energy levels. When you actually do the QED calculation, where the electron is continually emitting and reabsorbing virtual photons, and the vacuum is constantly fluctuating, the predicted energy shift lines up with the experimental Lamb shift to ridiculous precision, on the order of 1 part in a trillion in some cases. That is beyond good agreement. That is, if this theory were wrong, it would already be dead. But the vacuum is not done showing its hand. It also tweaks the electron's magnetic properties. A free electron behaves like a tiny bar magnet. The simplest theory gives a specific value for how strong that magnet should be relative to the electron's spin. That value comes out of the Dirac equation. When you measure it very carefully in a lab using trapped electrons and magnetic fields, you find a small discrepancy. The real electron's magnetic moment is slightly larger than the Dirac prediction by about 1 part in 1,000. Again, QED steps in with virtual photons. The electron interacts with its own electromagnetic field, the vacuum throws in loops of virtual particles, and the net effect is that the magnetic moment gets corrected. You can draw these corrections as Feynman diagrams with the electron line emitting and reabsorbing virtual photons again and again. When you add up the contributions from these processes, the theory predicts a corrected magnetic moment. That corrected value matches the experimental measurement to better than 1 part in a trillion. You are now at a level where theory and experiment agree to out to something like 13 decimal places. This is one of the most precise agreements between calculation and measurement in the entire history of science. And what is doing the work here? Photons, not real, on-shelf photons you detect as light, but virtual photons, mediating interactions, filling in loops, and representing the influence of the vacuum field on the electron. So when you say vacuum, you can't honestly mean dead nothing. Even when there are no real photons, the electromagnetic field still has zero-point energy. That energy depends on boundaries and conditions, and the differences create forces like the Casimir effect. It tweaks atomic levels, producing shifts like the lamp shift. It modifies the behavior of electrons, showing up in their tiny magnetic details. All of this has been checked in experiments with never-ending improvements in precision, and the same story keeps winning. The vacuum is active, and photons, even virtual ones, are central to that activity. That leads to a serious challenge. If the vacuum is buzzing with electromagnetic fluctuations, how do you ever say, "I caught a single real photon"? When your detector clicks, how do you know that was a genuine field excitation flying in from your source and not just some random fluctuation or device artifact? And how do we build devices that can pick up those single quanta clearly enough to do all the double-slit, delayed choice, and entanglement experiments you've heard about? Answering that means going right down into the hardware, the photomultipliers, avalanche diodes, CCDs, and telescope sensors that convert tiny, indivisible lumps of field energy into electric signals you can count. That is how we know we are seeing photons as discrete events, not just fooling ourselves with noise. How do you take one tiny photon, something that carries less energy than you can even feel, and turn it into an electrical signal strong enough to register on a machine sitting a meter away? That is the job of a single photon detector. And if these devices did not work as cleanly as they do, half of modern quantum physics would just collapse. In very low light experiments, people use things like photomultiplier tubes and avalanche photodiodes. The basic idea is simple but brutal. One photon hits, one electron responds, and then that one electron sets off an avalanche of more electrons until you get a big enough pulse to measure. In a photomultiplier tube, the inside is evacuated and the inner surface has a photocathode material. A photon hits that surface, knocks out one electron, and that electron is accelerated towards a series of electrodes, each time knocking loose more electrons from the metal. After a chain of maybe 10 or 12 stages, you can go from one starting electron to millions. That looks like a sharp spike of current on your electronics, a clear click. Avalanche photodiodes do a similar trick inside a piece of semiconductor. You reverse bias the diode so that any free electron falling through the junction region gets accelerated hard enough to slam into atoms and free more electrons. One photon creates one electron hole pair, and that one pair starts a chain reaction, a kind of controlled electrical avalanche. At the end of that avalanche, ohmic resistors and readout circuits translate the surge into a voltage pulse. Because your dark noise, the random pulses with no real photon, can be kept down to a few counts per second, and real signals under illumination can be thousands or millions of counts per second, you get a clean separation between nothing happened and a photon arrived. The detectors are not perfect. Some photons are missed, some dark pulses sneak in, but when you calibrate accurately, you can subtract background and see that the stats match quantum predictions, not some messy thermal instability. If this were just noise, the double-slit patterns, the Bell tests, the Hong-U-Mandel dips, all of that would smear out. They do not. The click patterns stay sharp enough that you can literally see quantum interference in the count rates. So that is the high-end lab gear. But what about the detector you carry all day in your pocket? Is your phone really doing something related, or is that just marketing hype about quantum sensors? Here's the uncomfortable answer. Your phone camera is absolutely a photon counter, just not operated in the extreme low light regime. In a CCD or CMOS sensor, the surface is divided into pixels, each just a few micrometers across, so a few millionths of a meter, a fraction of a human hair's width, or a few 10,000ths of an inch. Each pixel is essentially a tiny potential well in silicon. When a photon with enough energy hits, it can free an electron from a bound state into the conduction band. That free electron then sits trapped in that pixel's well. You expose the sensor for some fraction of a second. During that time, photons arrive. Each one that gets absorbed can free an electron. The number of electrons stored in that pixel at the end of the exposure is proportional to the number of photons that hit it. Then you read the sensor. Electronics shift out the charge from each pixel in a controlled pattern, convert that charge into a voltage and then into a digital number. Over a wide range, that number scales linearly with photon count. Double the photons, double the stored charge, double the digital value, until you saturate the pixel. Under normal daylight, each pixel is collecting huge numbers of photons per frame, so you never see individual events as separate steps. But when you crank the exposure time up and the light level down, the sensor output starts to look grainy. That grain is shot noise, the statistical fluctuation in how many photons happen to arrive in each time window. Astronomical CCDs push this further, cooling the chips to reduce thermal noise so they can see very small changes in photon counts. At that point, you're one engineering tweak away from doing single photon counting in exactly the same material you use in your phone. So detectors convert photons into electrons and electrons into voltage pulses. But can they handle signals where only a handful of photons show up per second from the other side of the universe? In modern astronomy, the answer is yes. Take a 10-meter class telescope with a mirror about 10 meters in diameter, roughly 33 feet. That mirror gathers light from distant galaxies that might be billions of light years away. For the faintest of these sources, you're sometimes down to just a few photons per second or even less, falling into the telescope at specific wavelengths. Each time one of those photons reaches the detector in the focal plane, it frees a charge packet in a single CCD pixel or fires a single avalanche pulse. The observatory records not just the spatial pattern, but also the time of arrival, down to fractions of a second or better. Over minutes to hours of exposure, you end up with a two-dimensional map of counts. Brighter areas on the sky send more photons, so more hits accumulate in those pixels. Darker regions send fewer. What your eye eventually sees as a smooth image of a galaxy, a nebula, or a cluster is literally built from millions of single photon detections stacked together. This is the same accumulation logic you saw in the double-slit experiment. One photon at a time arrives as a discrete event. Only when you add them up do they form a smooth pattern that looks like an object. There's no way to fake that with a purely classical wave that delivers energy in arbitrary small pieces. The statistics of the counts betray the fact that the energy is arriving in fixed chunks. Now push the timing to the limit. What happens if you not only count photons, but also timestamp them down to fractions of a billionth of a second over distances of tens of meters, tens of yards? Labs do exactly that in time-resolved photon experiments. They use very fast electronics and detectors with response times in the nanosecond or even picosecond, so billionth or trillionth of a second. They send photons through beam splitters, fibers, and interferometers spread over a few meters or dozens of meters, and then they log every arrival with its time tag. By comparing these arrival times across different detectors, they can check whether photons tend to arrive together, bunching, or avoid arriving together, anti-bunching. If photons were just classical particles arriving randomly, the statistics would follow a simple Poisson distribution. You could predict the chance of getting 0, 1, 2, or more photons in a given time window, and the correlations between different detectors would follow a specific pattern. In reality, when you use single photon sources and carefully designed optical setups, the measured correlations deviate sharply from those classical expectations. You see anti-bunching when a true single photon source is used. The chance of detecting two photons at almost the same time drops compared to random. You see bunching in thermal light sources, where photons tend to clump more than a purely random stream would suggest. These deviations are not small. They line up exactly with quantum predictions for the second-order correlation functions, the tools used to describe how detection events are related in time. This is the same kind of data that goes into Bell inequality tests, where detectors separated by tens of meters or more show correlations that no local classical model can match. You're not just using detectors as passive clickers, you're using them as probes of the underlying statistics, and those statistics refuse to be classical. So at this point, you have solid hardware that turns single photons into reliable electrical signals. You have telescopes catching individual quanta from galaxies billions of light years away. You have timing electronics that tell you exactly when each photon hit and how those hits cluster in time. None of that makes sense unless photons are real, discrete excitations of a field, not just convenient language for a fuzzy continuous wave. And once you have all that, you can try something more extreme. You can not only create single photons on demand, you can create pairs of photons whose properties are linked so tightly that measuring one immediately tells you something about the other, even if they are tens of kilometers apart. That is entanglement. And when you do it with photons, you run straight into questions about whether reality is local, whether it is deterministic, and what it even means to have a property before you look. You measure one photon here, and the outcome lines up with what someone else sees for another photon tens of kilometers away. You did not send a signal. You did not give it instructions, but the clicks line up in a way that regular physics just cannot explain. That is what entangled photons do, and there is no way to get rid of this without throwing out everything you have learned so far. Start with how you actually create these pairs. One of the standard tools is called spontaneous parametric downconversion. You take a laser, usually in the ultraviolet or blue part of the spectrum, so each photon carries more energy than a visible photon. You focus that beam into a special crystal, called a nonlinear crystal. The word nonlinear here means the crystal's response to the electric field of the light is not just proportional to the field strength, it includes higher order terms. Under the right conditions, that lets one incoming high-energy photon turn into two lower-energy photons. Energy has to be conserved, so the total energy of the two output photons adds up to the energy of the input photon. Momentum also has to match. That means the directions and wavelengths of the outgoing pair are linked. If one photon comes out slightly to the left, the other one goes slightly to the right in a way that keeps the total picture balanced. You set up the angles, the crystal temperature, and the laser wavelength so that the emitted pairs come out in clean cones or beams you can collect. You can engineer this process so the two photons are entangled in polarization, direction, or emission time. For polarization entanglement, you arrange the crystal and filters so that each individual photon is in a mixed state, but the pair as a whole has a definite combined property. You do this with micrometer precision in crystal orientation and beam alignment, and nanosecond precision in timing, because you need to be sure that the two photons really came from the same event, and not from two independent laser photons. When you detect one photon on one side and its partner on the other, you then look at how their polarization measurement results correlate. At this point, a classical thinker might try to cheat. You could say, maybe the photons carry hidden instructions from the source. When they are created, they get a shared list of answers for any measurement you might do later. They separate, but each one just consults its own copy of the list. That sounds reasonable, and if that were allowed, you could keep a basically classical idea of reality just with some extra hidden variables you do not directly see. This is where Bell tests crush that hope. John Bell derived a set of inequalities that any local hidden variable theory must satisfy. Local means nothing influences anything faster than light speed. Hidden variable means particles carry predetermined instructions that decide measurement outcomes. If the real world follows that template, then certain combinations of correlation numbers from polarization measurements must fall within specific bounds. In an entangled photon Bell test, you send each photon of a pair to a different station, separated by distances from a few meters up to tens of kilometers, so tens of miles. At each station, you have a polarizer that you can set to different angles. You choose these angles randomly and independently for each pair, often using fast electronics and random number generators, so the choices are made after the photons are already on their way. Then you record whether each photon passes or is blocked, basically a yes or no, or plus and minus. When you collect enough pairs, you compute the correlations between the results for different combinations of polarizer settings. The raw stats do not obey Bell's inequalities. Instead, they match the stronger correlations predicted by quantum mechanics, up to a limit known as the Siricellan bound. The violations are not small. They're big enough that experimental uncertainties and noise cannot cover them. Repeated experiments close different possible loopholes: detector inefficiency, timing, signal leakage. The result is the same. Any model where photons carry preset answers and nothing travels faster than light is incompatible with what the detectors actually see. So now you're forced to accept that when you measure one photon's polarization, you're not just revealing a pre-written value, you're part of a joint process that involves both photons even when they are far apart. The outcome on one side is strongly tied to the outcome on the other in a way that no local classical story can reproduce. People didn't stop at just testing this. They started using entanglement as a tool. One of the flagship protocols is quantum teleportation. Here's what that really means, stripped from sci-fi language. You have a photon A whose state you want to transfer. You have a pair of entangled photons, B and C. Photon B sits next to A. Photon C is sent down an optical fiber or through free space to a receiver, maybe tens of kilometers away, maybe up to a satellite hundreds of kilometers above Earth. At the sender station, you perform a special joint measurement on photons A and B. That measurement does two things at once. It destroys the original state of photon A, and it projects photon C far away into a new state that depends on the original state of A and on the result you just got. You then send two classical bits of information, using normal signals at or below light speed, telling the receiver which result you saw. The receiver uses that information to apply a small correction to photon C. After that, photon C is in the state that photon A used to be in before it was measured and destroyed. No physical photon traveled faster than light. No signal outran light. But the state, the pattern of quantum probabilities, has been recreated at a distant location without having to copy it in the classical sense. This has been done over optical fibers tens of kilometers long and between ground stations and satellites hundreds of kilometers apart. The success is measured by fidelity, a number between 0 and 1 that tells you how close the reconstructed state is to the original. Values above 80 or 90% in real experiments show that this is not noise. The entangled photons and the teleportation circuit are doing exactly what the quantum rules say they should. With that level of control, it is tempting to think, wait, if measuring one photon over here has such tight connections to the other one out there, can I use this to send messages faster than light? That would break relativity. So if that were possible, your whole picture of space-time would fall apart. But when you dig into the numbers, you see a hard limit. Look at one detector alone, without comparing to the other side. The clicks you see are random. You cannot tell from your local data only whether the other observer changed their polarizer setting or not. The distribution of results on each side separately does not depend on what the other side does. The spooky correlation only appears when you bring the records together and compare them. That comparison requires ordinary communication at or below the speed of light. So entangled photons give you non-local correlations, but not non-local control. You cannot send a bit with them faster than light. They obey relativity in what they allow you to do, even while completely breaking your classical picture of local hidden properties. By now, the word photon should mean something very different from tiny bullet of light. You are dealing with non-local, correlated excitations of a field that can tie measurement outcomes together across tens of kilometers, with timing controlled down to nanoseconds, using real hardware, crystals, lasers, optics, and detectors. You test the limits of classical ideas, they fail. You test quantum predictions, they pass again and again. The old picture of individual, independent particles just moving through empty space is gone. Photons come in entangled pairs and networks. The vacuum never sits still, and the field viewpoint works from the smallest lab setups all the way out to the scale of the whole universe. So the next step is to zoom way out. If photons can link events across labs and cities, what are they doing across billions of light years? How are they storing information about the early universe, about the Big Bang, about the first atoms forming in a way that still reaches you today? And how can a cold sea of ancient photons, stretched by cosmic expansion, still dominate the particle count of the universe you live in right now? Every direction you point a good enough detector, the universe is glowing. And it's not from stars, galaxies, or anything you'd call objects. It's from a wall of ancient photons that have been flying almost since the beginning of time, and they are still hitting you now. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. Before that, space was a hot plasma. Photons kept bouncing off free electrons, constantly scattered, unable to travel far without being redirected. When neutral atoms formed, the fog cleared. Photons could finally move in straight lines for huge distances without being constantly scattered. A huge number of them took off across the universe at that moment, and they basically never stopped. Those photons are still around today. They have cooled with the expansion of space and now form what we call the cosmic microwave background, the CMB. If you plot how many of those photons you get at each frequency, you get a spectrum that is almost a perfect black body curve at a temperature of about 2.725 Kelvin, just a couple of degrees above absolute zero. The peak of that curve sits at wavelengths around 1 millimeter, about 0.04 inches, in the microwave part of the spectrum. Satellite missions like COBE, WIMAP, and Planck mapped this background across the whole sky. They measured its temperature, not just to tenths of a Kelvin, not just to thousandths of a Kelvin, down to microkelvin, millionths of a Kelvin. When you look at the raw map, the CMB is astonishingly uniform, the same temperature in every direction to 1 part in 100,000. On top of that, you see tiny fluctuations, hot and cold spots with temperature differences of tens of microkelvin. Those small pattern differences are the seeds of all the structure in the universe today. So how many of these relic photons are you dealing with? The answer is an absurd number. There are roughly a billion CMB photons for every proton in the universe. Take a cubic meter of space, a box 1 meter on a side. On average, that box contains maybe a few atoms, a handful of baryons. But in the same cubic meter, you have about 400 CMB photons. If you convert that to a cubic foot, you still have hundreds of background photons in that volume. They're cold, they're low energy, but they dominate the particle count. In terms of sheer number, the universe is photon country, not matter country. That photon to baryon ratio matters because it tells you how tightly coupled radiation and matter were in the early universe. When the universe was very hot and dense, that sea of photons pushed on the plasma, resisted compression, and set up sound waves in the early cosmic fluid. The imprint of those waves shows up today in the pattern of hot and cold spots in the CMB map. The fact that there are so many more photons than baryons is a direct reason why those early oscillations behave the way they do. Now, bring in expansion. As the universe grows, space itself stretches. Photons ride along with that expansion. Their wavelengths stretch with the scale of the universe. A photon that started out with a wavelength in the visible or ultraviolet range, maybe a few hundred nanometers, can, after billions of years of expansion, arrive at your telescope in the infrared or even microwave band, with wavelengths stretched by factors of 2, 5, 10, or more. This stretching is what astronomers call redshift. You measure it by looking at known spectral lines, fingerprints of elements like hydrogen, helium, oxygen. Those lines have precise rest wavelengths measured in nanometers or angstroms. When you observe a distant galaxy, you see those same lines shifted toward longer wavelengths. The ratio between observed and rest wavelength tells you the redshift, usually written as Z. A redshift of 1 means the wavelength has doubled. A redshift of 6 means it has been stretched by a factor of 7. Cosmological models take that redshift and connect it to distance and look-back time using the expansion history of the universe. So for distant galaxies in the CMB, photons are not just messengers, they're rulers. Their stretching is how we measure how much the universe has expanded since they were emitted. You are literally reading cosmic history out of the wavelengths of the photons that hit your detectors right now. But the CMB is more than just a temperature and a frequency curve. Those photons are polarized, and that polarization pattern holds even more information. Remember polarization from earlier? It's the direction the electric field oscillates, perpendicular to the direction of travel. The CMB photons picked up and modified their polarization by interacting with electrons in the early universe and by passing through large-scale structure later on. When you map polarization across the whole sky, you can break the pattern into two types, called E modes and B modes. E modes are patterns that look like gradients, radial or tangential alignments around hot and cold regions. B modes are curl-like patterns, like little swirls. Experiments scan large chunks of sky, measure polarization angles, and extract these components with sensitivity again down to microkelvin in polarization temperature. The E-mode pattern tells you about density fluctuations in the early universe and the physics of recombination, when those photons were last scattered. It also encodes how matter moved under gravity as structures grew. B-modes can be generated by gravitational lensing, where massive structures like galaxy clusters bend photon paths and twist their polarization. On top of that, there might be a very faint B-mode signal from primordial gravitational waves, ripples in space-time from the first fractions of a second after the Big Bang. If detected cleanly, that would be a direct sign of physics at energy scales far beyond what any Earth-based accelerator can reach. The key point is, all of this comes from photons, cosmic background photons with wavelengths of millimeters, traveling for around 13 billion years, now arriving at detectors that sit on satellites, balloons, and Antarctic ice. Their energies are tiny, but because there are so many of them and because we can measure their distribution and polarization so precisely, they become a hard data set on the entire history of the universe. So now connect this to your earlier picture. Photons are not just lab toys for double-slit experiments and entanglement demos. They are fossils from the early universe, still carrying detailed information in their frequencies, directions, and polarization patterns. They tell you how hot the universe was, how fast it expanded, how matter clumped, and maybe even how space-time behaved at timescales far shorter than a nanosecond after the Big Bang. But the story is not limited to cold microwaves. At the other end of the spectrum, photons mark out the most violent events the universe can make: matter falling into black holes, neutron stars colliding, and gamma-ray bursts that outshine entire galaxies. Those extreme photons in X-rays and gamma rays push your detectors, your telescopes, and even your theories to their limits. So the next step is to go from the quiet background bath to the sharp spikes, from the smooth CMB glow to the brief, intense flashes that signal black holes feeding, neutron stars tearing themselves apart, and jets punching out of galaxies at close to light speed. How do photons behave there, near horizons and in magnetic fields so strong they can rip atoms apart? And what do those extreme photons tell you about gravity, matter, and space-time when they're pushed right up against their breaking points? How far can a photon be pushed before your usual ideas about light and gravity just snap? Out in the universe, you don't have gentle sunlight and soft microwaves. You have photons fired out of places where space-time itself is bent almost to breaking. Start with neutron stars. Take more than the mass of the sun, crush it into a sphere about 10 kilometers across, roughly 6 miles. The surface gravity there is insane, tens of billions of times Earth's. Matter falling onto that surface doesn't bump, it slams in at a significant fraction of light speed. As it hits, it heats up to tens of millions of Kelvin, and at those temperatures, the dominant photons are X-rays with energies in the kilo-electron-volt range, thousands of electron volts per photon, far beyond visible light. We see these objects as X-ray pulsars. The neutron star is rotating, sometimes dozens or hundreds of times per second. Its magnetic axis is tilted relative to its spin axis, so the hotspots where matter hits are not aligned with the rotation. As the star spins, those hotspots sweep past your line of sight like lighthouse beams, and your X-ray detector on Earth or in orbit sees pulses. Observatories measure these pulse periods down to milliseconds, thousandths of a second, and track tiny changes as the star accretes matter or loses angular momentum. On top of that, the gravity is so strong that it redshifts the photons. A photon climbing out of that gravitational well loses energy. Its wavelength stretches. Spectral lines that you know from lab measurements should appear at specific energies, arrive shifted to lower energies. For iron atoms on the surface, the X-ray lines that should be at a particular kilo-electron-volt value are displaced. The shapes of these lines and the way the pulses smear out in time tell you that photon paths near the surface curve dramatically. Light that leaves the back of the star can be bent around so you still see it. You are literally mapping space-time near a collapsed object just by watching how photons arrive. Then you crank things up again and look at gamma-ray bursts. These are not steady beacons, they are brutal flashes. A gamma-ray burst can release around 10 to the power of 47 joules in a few seconds. That's comparable to what the sun would emit over billions of years, dumped almost all at once, mostly as very high-energy photons. Satellites like Fermi sit in orbit watching the sky for these spikes. When one hits, the detectors register photons with energies up to tens of giga-electron volts, tens of billions of electron volts per photon. If you zoom into the time series, you do not see a smooth glow. You see structure on millisecond scales. Different energy bands rise and fall at slightly different times. The spectrum changes shape as the burst evolves. And then, after the initial blast, you get an afterglow that can last for days or weeks. That afterglow shows up across the electromagnetic spectrum: X-rays, ultraviolet, visible, infrared, radio. By tracking how the brightness and spectrum change, you infer collisions of relativistic jets with surrounding gas, shock waves, and magnetic field structures at distances of light years, trillions of kilometers from the central explosion. All of that information is carried to you on photons that survived one of the harshest environments nature can build. Black holes push the picture even further. A black hole itself emits no light from inside the event horizon, but the matter spiraling into it forms an accretion disk. In that disk, friction and magnetic turbulence heat the gas to extreme temperatures. Photons produced close to the event horizon have to climb out of a deep gravitational well. Their energies and paths are warped by the curved spacetime. One clear signature is the iron K-alpha line, which in the lab appears at about 6.4 kilo-electron volts. In X-ray spectra from gas swirling near supermassive black holes, that line does not show up as a sharp spike. It appears broadened and skewed, stretched to lower energies on one side. That distortion encodes the combination of Doppler shifts from gas moving at a large fraction of light speed and gravitational redshift from photons trying to escape near the horizon. By fitting these line profiles, astronomers estimate how close to the event horizon the emitting material is, often just a few gravitational radii away. Further out, jets shoot out along the black hole's spin axis, powered by magnetic fields and rotation. Radio telescopes see these jets over distances of light years, which is about 10 trillion kilometers per light year, or about 6 trillion miles. The radio and X-ray photons we pick up are synchrotron radiation, produced by electrons spiraling in strong magnetic fields at nearly light speed. The brightness, polarization, and structure of those photon streams give you direct constraints on the magnetic geometry and particle energies in regions your spacecraft will never reach. Even when high-energy photons do not reach the ground, they still leave signatures. Ultra-high-energy gamma rays and cosmic rays slam into Earth's atmosphere at energies far beyond anything our accelerators reach. When one of these hits an air molecule, it sets off a cascade, a shower of secondary particles and photons racing downward. Some of those charged particles move faster than light travels in air. That is allowed because light in air moves slightly slower than in vacuum, roughly 99.97% of c, about 0.9997 times 300 million meters per second. When a particle exceeds that speed in air, it emits a brief cone of blue Cherenkov light, a kind of optical shockwave. Cherenkov telescopes sit on the ground with large mirrors, sometimes arrays covering square kilometers, square miles. On dark nights, they watch patches of sky and look for those faint blue flashes in the atmosphere. By analyzing the timing and brightness pattern across different detectors, they reconstruct the direction and energy of the original photon or particle that started the shower. This way, they can study gamma rays with energies so high that a single photon can carry as much energy as a pitched baseball, tens of joules, far beyond what normal detectors could withstand directly. Across all these cases, the same theme keeps hitting you. Photons are not passive messengers. Near neutron stars, they map extreme gravity and dense matter. In gamma-ray bursts, they carry out signatures of jets, shocks, and magnetic fields evolving over milliseconds. Around black holes, their energies and line shapes tell you how space-time behaves only a few gravitational radii from an event horizon. In Earth's atmosphere, they mark the impact of particles and photons with energies that push your theories to their very edges. And this cuts both ways. On one hand, extreme astrophysical environments test your understanding of photons and fields in conditions you can't build on Earth. On the other hand, your entire technological civilization leans on the same quantum electrodynamics that explains those distant signals. Lasers, GPS, fiber optic cables, quantum devices. All of them are practical, local applications of the same photon as field quantum story that lets you read the universe. So the next question is, if photons can survive near black holes and carry clean information across billions of light years, what exactly are they doing inside the gadgets in your pocket and on the satellites above your head? How do the same rules that describe gamma-ray bursts also show up in a cheap laser pointer, in an atomic clock keeping GPS in sync, and in quantum key distribution systems trying to keep your data safe? Right now, you are surrounded by devices that quietly bet your safety, your money, and your sense of "where am I?" on photons behaving exactly like quantum field theory says they should. If photons were even slightly different, your GPS would lie, your internet would choke, and your laser pointer would be useless decoration. Take the laser first. When you click a cheap laser pointer, you're not just turning on a red light. You're creating a beam where an absurd number of photons share almost the exact same state. Same frequency, so same color. Same direction, so they march in a tight, straight beam. Same phase, so their wave crests and troughs line up. That is coherence. A typical low-power laser pointer might output a few milliwatts, so a few thousandths of a watt, at a visible wavelength. Turn that into photon language, and you're looking at around 10 quadrillion photons per second. That's 10 to the power of 16, leaving that tiny aperture every second. Because they're coherent, you can send that beam across meters or tens of meters, even hundreds of meters in clear air, and still see sharp interference patterns if you split and recombine it. In labs, coherent beams bounce along paths with length differences of kilometers and still interfere predictably. That only makes sense if each photon is a field excitation that can stay in phase with its neighbors over long distances, not a bunch of independent bullets. Holography, precision distance measurements for gravitational wave detectors, and ultra-stable interferometers for navigation all lean on that. If the photon equals quantized field mode picture was even slightly off, these interference fringes would wash out and all that tech would fail. Now, how tight is the control we can get on photon frequency? Tight enough that your position on Earth is inferred by counting cycles of light-like oscillations to absurd precision. Atomic clocks do this. They pick a specific transition in an atom, a jump between two internal energy levels, and lock a microwave or optical photon source to match it exactly. For cesium, the standard is a hyperfine transition whose frequency has been defined, by agreement, as 9,192,631,770 cycles per second. That is the tick of the clock. GPS satellites carry these atomic clocks on board. They continuously broadcast signals tied to their internal photon-based timing. Your phone or car receiver listens to several satellites at once and measures how long each signal took to arrive. Since light moves at about 300,000 kilometers per second, or about 186,000 miles per second, even a tiny timing error matters. A delay of 10 nanoseconds, 10 billionths of a second, corresponds to about 3 meters of distance, roughly 10 feet. A few tens of nanoseconds of error, and your indicated position can jump a lane on the highway or onto the wrong side of a street. To keep that under control, the photon frequencies in the atomic clocks have to be stable to parts in 10 trillion or better. On top of that, engineers correct for relativity. Clocks in orbit tick faster than clocks on Earth's surface because of both gravitational and velocity effects. If they didn't correct for that, GPS errors would accumulate to kilometers per day. You only get stable location services because photons obey the same energy-frequency relationship up in orbit and down here. Then there's the wiring of the modern world. Optical fibers. Under your feet and under the oceans, photons are racing through glass strands, carrying your video calls and financial transactions. In fiber, light travels slower than in vacuum because the refractive index of glass is higher than 1. The speed is roughly 200 million meters per second, about 186,000 miles per second. Over 1,000 kilometers, a signal takes about 5 milliseconds to arrive. Data centers and stock exchanges care about those milliseconds. Losses in good fiber are only a few decibels per tens of kilometers, so signals can run for hundreds of kilometers with amplifiers and repeaters, and undersea cables can cross oceans with chains of amplifying stations. But to make this work, engineers have to treat photons both as quantum objects and as classical waves. Each bit you send is encoded into properties of a light pulse: amplitude, phase, frequency, or polarization. Quantum effects like shot noise and no cloning set hard lower limits on how weak the signals can be and how much you can amplify them without adding noise. Classical wave effects like dispersion and nonlinearity stretch and distort pulses as they travel. Both have to be modeled and corrected. If photons were classical particles, you might try to duplicate them perfectly to beat noise. If they were classical waves with no quantum graininess, shot noise would not be an issue. In reality, the fact that light arrives in discrete quanta and that you cannot copy an unknown quantum state exactly is baked into how you design fiber systems and amplifiers. That same quantum no cloning rule is not just a headache, it's also a weapon. That's what quantum key distribution uses. Instead of sending many photons per bit and just hoping no one eavesdrops, you deliberately work in the single photon regime. You encode bits into polarization, for example, horizontal and vertical for 0 and 1 in one basis, diagonal and anti-diagonal for 0 and 1 in another basis. Protocols like BB84 tell you exactly which states to use and how to choose bases randomly. Here's the key. If an eavesdropper tries to intercept and measure these photons, they cannot copy the states and forward perfect clones. Any measurement they make collapses the state into something definite in their chosen basis. If they guess the wrong basis, they disturb the photon. When you and your communication partner later compare a subset of your data over a normal channel, you see an error rate higher than what random noise alone would produce. That spike in errors is the signature of someone tampering with your photons. If the error rate stays low, you can be confident that the key you distilled from the measurements is secure. This has been done over hundreds of kilometers of optical fiber and via free space links to satellites hundreds of kilometers up. The actual numbers matter. Bit error rates, key rates and bits per second, and the level of disturbance you accept before you declare the channel compromised. And under all of that sit single photons with specific polarizations and arrival times, processed by detectors that have to distinguish real clicks from dark counts with extreme reliability. So your pocket laser, the satellites that tell you where you are, the fibers under the sea carrying your data, and the quantum cryptography experiments trying to secure that data all depend on the same underlying facts. Photons are quantized excitations of a field. They have fixed relationships between energy and frequency. They cannot be cloned perfectly, and their statistics take over when signals get weak. That still leaves out one more property that matters both out in space and here on Earth. Photons carry momentum. They can push on things. In space, that means you can literally sail on light. In labs, you can trap and move microscopic particles with nothing but a focused beam. And in astrophysics, radiation pressure helps shape dust disks and drive stellar winds over distances of millions of kilometers and millions of miles. So the next question is blunt. If photons have no rest mass, how can they still deliver a shove? How does a beam that seems intangible from your point of view slowly change the path of a spacecraft or hold a tiny bead steady in an optical trap? And what does that tell you about how energy and momentum really flow in a field that fills all of space? You keep hearing photons have no rest mass, so it's easy to assume they can't shove anything. But they do. They hit, they bounce, and they transfer momentum. And if you give them enough time and enough surface area, they will absolutely move real hardware through space. Start with the basic idea. A photon carries energy, and anything that carries energy moving at light speed also carries momentum. The amount is small, it's equal to the photon's energy divided by the speed of light, but small per photon doesn't matter when you have insane numbers of them. At Earth's orbit, the sun dumps about 1.3 kilowatts of power into every square meter facing it, a bit more than 1,000 watts per square meter. If you take that stream of photons and let it hit a surface that absorbs everything, you get a small push. If that surface reflects perfectly, you get roughly double the push, because photons reverse direction and give back more momentum. Do the numbers and you get a maximum radiation pressure of about 9 micronewtons per square meter at Earth's distance for a perfectly reflecting surface directly facing the sun. 9 micronewtons is 9 millionths of a newton. On Earth, that's comparable to the weight of a microgram scale mass per square meter, way less than a single grain of sand. It sounds pathetic, but it's steady, it's free, and in a low-friction environment like space, you don't need much acceleration to get serious speed over time. We can actually measure this tiny push on Earth using torsion balances. You hang a mirror or a light, thin vein on a very sensitive fiber, shine a known light beam on it, and watch it twist. The torque you measure matches what you expect from photon momentum. The effect is not a theory-only curiosity, it's a lab-level measured force. Turn off the light, the torque dies. Turn it on, the twist reappears. That is radiation pressure in action. Now scale that up and put it on a spacecraft. Solar sail missions do exactly this. They deploy large, thin, reflective sheets tens of meters across, so tens of yards. A sail might have an area of hundreds of square meters, so hundreds of square yards, but a total mass of just a few dozen kilograms. The sun's photon stream hitting that mirror gives a constant, gentle push. Typical accelerations are in the range of fractions of a millimeter per second squared. For example, 0.5 millimeters per second squared, which is around 0.0002 inches per second squared. That's tiny, but space has effectively no air drag and very little resistance. Over days and weeks, that slight acceleration modifies a spacecraft's orbit. Over months and years, it can build up to significant velocity changes, hundreds or thousands of meters per second. Mission data show trajectory changes that match the prediction from solar radiation pressure, not from any onboard thrust. That means photons, not propellants, are doing the work. The spacecraft is literally changing path because starlight is pushing on it. The equations of motion fit the light as momentum carrier model, and they do not fit no pressure models. The same physics works on microscopic scales, but with much tighter control. Optical tweezers are a good example. You focus a laser beam very tightly using a high numerical aperture lens. That creates a very strong intensity gradient in a tiny region, about a micron across, about the size of a bacterium. When a small dielectric bead or a biological cell sits in that region, the way light refracts through it creates forces that pull the object toward the highest intensity point. It's like a little trap made of photons. The forces involved are in the femtonewton to piconewton range. A femtonewton is a millionth of a billionth of a newton. A piconewton is a trillionth of a newton. Those are extremely small, but with careful calibration, by tracking how far a bead is displaced in a known trap stiffness, you can measure and apply those forces precisely. Researchers use optical tweezers to grab single DNA strands, to measure the strength of protein bonds, to move organelles inside living cells by nanometers at a time, billionths of a meter. None of that works unless photons really do transfer momentum and create mechanical forces that you can measure, control, and repeat. On astrophysical scales, radiation pressure is not just a lab curiosity, it helps sculpt whole systems. Starlight hitting dust grains in a protoplanetary disk exerts a small outward force. For very small grains, comparable to or smaller than the wavelength of the light, that force can compete with gravity. Some grains get pushed outward, some get blown out of the system completely, depending on size and composition. When we look at disks around young stars in infrared and radio images, the distribution of dust, the formation of gaps and rings, and the balance between inward gas drag and outward radiation pressure all have to be modeled together. The patterns we observe match models where photons play an active role, not just as passive illumination, but as agents reshaping orbits over millions of years. Radiation pressure also helps drive stellar winds. In very luminous stars, photons interact with ions in the outer layers. Each absorption and re-emission event transfers a tiny amount of momentum. Summed over the enormous photon flux from a bright star, that adds up to a net outward force that can strip off material. Observed mass loss rates and wind speeds in hot, massive stars line up with models that include photon-driven acceleration. Again, massless photons are doing the pushing, over distances measured in astronomical units, tens or hundreds of millions of kilometers, tens or hundreds of millions of miles. So tie this back to your mental picture. A photon has no rest mass, it never slows below light speed, it has energy set by its frequency, and it has momentum equal to that energy divided by the speed of light. Individually, that momentum is tiny, but in huge numbers or applied over long times, it does real mechanical work. It twists torsion balances, pushes on solar sails, holds microscopic beads in place, shapes dust disks, and helps drive gas off stellar surfaces. At this stage, photons are doing everything. They're the stuff of your images, the timing signal for your clocks, the information carriers in your networks, and the pressure that can move objects from micron scales up to spacecraft and dust grains in orbit. It's tempting to think, okay, now I finally have a solid picture. Photons are just little packets of energy and momentum, and if I have many of them, I can treat them like a classical beam. But that is not the end of the weirdness. If you turn the knob in the other direction, away from big beams and towards very carefully prepared quantum states, even the number of photons stops being a simple, well-defined thing. You get beams where the phase is sharp but the photon number fluctuates, states where the noise in one quantity drops below what classical light can ever reach, and situations where photons show up in pairs or groups with statistics that no classical wave can mimic. So the next step is to look at light in these non-classical regimes. What happens when you force the field into a state with exactly one photon, or into a state where photon numbers fluctuate in a very specific way? How do you see that in real experiments, and why does it finally kill the last fallback idea that photons are basically classical just with some graininess? You'd think that once you say, okay, photons are little chunks of light, you're done. But when you look closely at how light is actually prepared in the lab, even the idea of how many photons are in this beam stops being a simple yes-no question. Start with something you know: laser light. A laser beam is not 10 to the power of 16 identical bullets per second. Quantum mechanically, the best simple description is a coherent state. In that state, the phase of the field is very well defined, so the crests and troughs of the wave are sharp, but the exact photon number is not fixed. It fluctuates. The probability of finding 0 photons, 1 photon, 2 photons, and so on in a small time window follows a Poisson distribution. That distribution has a specific property. The variance equals the mean. In plain language, you get random scatter but with a particular pattern. Now, compare that to an ideal single photon source. There, the goal is the opposite. You don't care about a stable phase, you care about having a definite photon number. 1. That's called a Fock state with photon number 1. In that regime, if you look on very short timescales, you should never see 2 photons arrive at once. The stream is as anti-bunched as it can get. Physicists quantify this using a correlation function called G2 of 0. You split a beam with a beam splitter, send the 2 outputs to 2 detectors, and you look at how often you get clicks at exactly the same time in both detectors. If light is a perfect coherent state like an ideal laser, you get G2 of 0 equal to 1. That means coincidences occur just like you'd expect for a Poisson process. If the light comes from a true single photon source, G2 of 0 drops towards 0. Coincidences at 0 time delay almost vanish because you never have 2 photons in the same pulse to split. Real experiments measure this by time tagging each click with nanosecond resolution and building up statistics. The data really does separate coherent from single photon light this way. So right there, you see that photon number is not just a fixed label. In coherent light, it fluctuates. In Fock states, it's sharply defined. In thermal light, it bunches more than Poisson. The same field can be in very different statistical states, and you can tell the difference by how the detection clicks cluster in time. It gets more extreme when you start squeezing. In ordinary light, quantum noise sets a hard lower limit on how precisely you can know amplitude and phase together. These two properties are like position and momentum for the field. Squeezed states deliberately reduce the noise in one of them at the expense of more noise in the other. You don't beat quantum mechanics, you reallocate the uncertainty. This is not just a theory exercise. Gravitational wave detectors like LIGO literally inject squeezed vacuum into their interferometers to push sensitivity beyond the usual photon shot noise limit. They have 4-kilometer arms, about 2.5 miles each, arranged at right angles. Laser light bounces back and forth along these arms between mirrors. Passing gravitational waves change the arm length by less than the diameter of a proton, around 10 to the minus 15 meters, and the detector infers those changes by watching interference fringes in the returning light. At these tiny displacements, the random arrival of photons, shot noise, becomes a limiting factor. By feeding in squeezed light, tuned so that the noise in the observable that matters for the measurement is reduced, LIGO gains a few decibels of sensitivity. That means it can see weaker gravitational wave signals from more distant sources. You are literally using a non-classical state of light with engineered noise properties to measure space-time vibrations passing through Earth. Now, go to one of the cleanest tests of photons are identical bosons, the Hung-O-Mondel experiment. Set up a beam splitter with 2 input ports and 2 output ports. Send in 1 photon from the left, 1 from the right, and ask, where do they come out? If they were classical, distinguishable particles, each one would have a 50% chance to be transmitted and a 50% chance to be reflected, independently. That would give you a 25% chance they both go to the top detector, 25% chance both go to the bottom detector, and 50% chance they split, one up and one down. What you actually see when the 2 photons are truly identical in every relevant way, same frequency, same polarization, same spatial mode, and their arrival times matched to with any fraction of their coherence time, is different. The split outcome almost disappears. The photons always exit together, both going out of the same port. That's called bunching. If you measure coincidences between the 2 detectors as you scan the relative delay between the photons, you get a dip that goes down towards 0 when the delays are matched within micrometers of extra path, which is a few femtoseconds of travel time. That dip, the Hung-O-Mondel dip, is not something you can fake with classical waves plus simple detector models. It reveals that the two-photon state is a superposition where the both transmitted and both reflected paths interfere, wiping out the one each outcome. It's a direct demonstration that photons obey bosonic statistics and that two-photon interference is a real, measurable effect. Once you can control interference between a few photons like that, you can try to use them as qubits in a computer. In photonic quantum computing, you encode information into properties of photons: polarization up or down, path left or right in a waveguide, or time bins early and late in a pulse train. Then you route these qubits through integrated optical circuits built on chips a few centimeters across. Those chips contain beam splitters, phase shifters, and interferometers etched into glass or semiconductor material. Two-photon and multi-photon interference at these on-chip beam splitters implement quantum logic gates. With a handful to a few dozen of photons, experiments have run small algorithms, simple versions of search, sampling tasks, or basic error correction codes. They measure gate fidelities, how close the operation comes to the ideal, and error rates, how often something goes wrong. The results show that at small scales, you can perform logic operations purely by lining up interference and detection patterns of photons. No moving electrons, no changing voltages in transistors, just field excitations entering, mixing, and being counted at the outputs. All of this adds up to a picture that is very far from photon as tiny ping-pong ball. The same beam can be in a coherent state, a squeezed state, a thermal state, or a number state. The number of photons can be sharp or it can fluctuate, and those fluctuations can be sub-Poisson, Poisson, or super-Poisson depending on the state. Photons can anti-bunch, bunch, interfere as pairs in non-classical ways, and act as qubits in fragile superpositions that only show up when you look at multi-photon correlations. So when you say there is a photon here, you're already glossing over a lot. Are you talking about a definite number state or about a fuzzy distribution? Are you ignoring entanglement with other modes? Are you pretending the vacuum is quiet? The word photon is convenient, but it hides most of the actual structure. What you really have is a quantum field in some state, and one photon is just one of the simpler labels you slap on part of that state when the detector clicks. That brings you to the final uncomfortable step. If light is a field, if electrons are fields, if every particle you've talked about is really just an excitation of some underlying field, then maybe photons aren't special at all. Maybe they're just the cleanest example. And the real thing you have to wrap your head around is not what is a photon, but what is a quantum field, and why does reality look like a bunch of particles when we measure it? To answer that, you have to pull everything together: the black body story, the double slit, measurement, relativity, fields, virtual photons, technology, and non-classical states, and ask what's left that you can honestly call a photon without lying to yourself. So, after all of this, what are you actually dealing with when you say photon? Run through the checklist in your head, and it sounds almost self-contradictory. A photon shows up at your detector as a single sharp click in one pixel or in one avalanche diode, never half a click here and half a click there. That is particle behavior. The same photon, if you trace its path through a double-slit setup, forces you to describe it as a wave spread out over both slits, interfering with itself over distances of meters, yards. That is wave behavior. It never sits still. It has no rest mass, so there is no photon at rest state you can even imagine. It always moves at light speed in vacuum, about 300,000 kilometers per second, roughly 186,000 miles per second. It carries energy that is set by its frequency through Planck's constant, and it carries momentum equal to that energy divided by the speed of light. It has spin, an internal angular momentum, even though there is nothing there you can point to and say, that is the bit that's spinning. It plays by relativity's rules so hard that in the limiting sense, it experiences no proper time between emission and absorption, while you watch it cross billions of light years over billions of years. It can be part of an entangled pair where a measurement here locks in correlations with a partner tens of kilometers away, yet it refuses to let you send signals faster than light. It is born and destroyed in interactions, emitted when an atom drops from one energy level to another, absorbed when another atom jumps up, created and annihilated in particle collisions. If you try to wrap all of that in a simple picture like tiny ball of light, you are lying to yourself. If you try smooth wave, you are also lying. The only picture that has survived every test, from cheap laser pointers to gravitational wave detectors to cosmic microwave background maps, is the field picture. The cleanest statement modern physics gives you is blunt. A photon is a quantized excitation of the electromagnetic field. That field fills all of space, all the time. When it's in a particular pattern of vibration with a specific frequency and spatial mode, its energy can only take discrete values. Going from one step on that energy ladder to the next is what you call adding one photon to that mode. Removing a step is absorbing one photon. In that framework, a photon has a well-defined energy, which is Planck's constant times its frequency. Its momentum is that energy divided by the speed of light. It always travels at light speed in vacuum. It is created and annihilated at interaction points, in a blackbody oven, at the surface of a star, in a fluorescent tube, in a parametric down-conversion crystal in a quantum optics lab. When you calculate scattering probabilities, spectral line strengths, decay rates, or cross-sections for electrons and ions interacting with light, you use quantum electrodynamics, the quantum field theory of the electromagnetic field. The numbers it gives match experiments to absurd precision, sometimes to 1 part in a trillion or better. So, if the math is this good, why does your intuition fight it so hard? Because your brain never had to deal with this regime while it evolved. Your everyday world is built on speeds of meters per second, feet per second. You throw a ball at a few tens of meters per second and catch it. You walk at 1 or 2 meters per second. Distances you care about are meters, yards, maybe kilometers and miles if you drive a long way. Energies you notice are in food calories and body heat, not in tiny joules per photon. Photons live in a world your nervous system never trained on. They move at 300 million meters per second. They act over nanometer scales in chips and molecules, and over gigaparsec scales between galaxies. Their energies at the level of individual quanta are around 10 to the minus 19 joules for visible light. That's not a range your senses can resolve. When you try to force this behavior into old categories, little balls flying along trajectories, or waves in some medium, you're squeezing an alien system into a Stone Age control panel. This is why physicists often fall back on a more cold-blooded way of talking. In practice, photon is partly a bookkeeping word. When energy and momentum flow through the electromagnetic field, you can count that flow in units. 1 unit is 1 photon at that frequency. If a detector clicks, you say a photon arrived. If a laser emits a beam with a known power at a given wavelength, you divide that power by the energy per photon and say that's about 10 to the power of 20 photons per second. Underneath, you're not imagining 10 to the power of 20 tiny marbles. You're using the photon count as a convenient way to talk about how much the field is excited. The field itself is what obeys the deep rules: commutation relations, uncertainty principles, the algebra that tells you how different modes and different points in space relate. The photon language rides on top of that, like how you talk about waves and surfers on an ocean without thinking about every water molecule. Once you accept that, you see that photons aren't special cases. Electrons are excitations of an electron field. Quarks are excitations of quark fields. The Higgs boson is an excitation of the Higgs field. Gluons are excitations of the gluon field. Every particle in the standard model is really just a particular field's quantum showing up at your detector, whether that detector is a silicon chip, a cloud chamber, a photomultiplier tube, or a giant array buried in ice or rock. So, asking what is a photon really pushes you toward a more brutal answer. Reality, as far as our best tested theories can see, is made of quantum fields. They stretch across space and time. They have ground states that are not truly empty, they fluctuate even in vacuum, and they can be excited in discrete chunks. Photons are just the excitations of the electromagnetic field, and because that field interacts with charged matter and travels long distances without getting stuck, photons are the excitations you deal with most directly. You see by them, you heat things with them, your devices run on them, and distant galaxies talk to you using them. The strangest part is that the deeper and more precisely we look, the more consistent this field A story becomes. From nanometer scale optical chips to 4-kilometer interferometers, from lab cavities a few millimeters wide to cosmic paths billions of light years long, photons keep behaving like quantized field modes, not like little classical bullets. Every time we push for more detail, the universe doubles down on that answer. So, no, a photon is not a comfortable particle of light the way a pebble is a particle of rock. It's a quantum of a field that fills all of space, that never sits still, that ignores your everyday intuitions about time and distance, and that still somehow gives you clean clicks on a detector. You don't just look at photons from the outside, you live in a universe structured by them, shaped by them, and constantly bombarding you with them, and they stubbornly refuse to fit into the old boxes your brain wants to use. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.